But in this class, we are going to have a special case of the spherically symmetric harmonic oscillator, but which is not something that fits into this description that we are doing today. And that special case is the isotropic harmonic oscillator. So what does it mean by isotropic? It means that it's it's a harmonic oscillator in every direction. So its Hamiltonian is given by p squared by 2m plus half of m omega squared r squared. And of course, p squared is given by px squared plus py squared plus pz squared, and r is given by x squared plus y squared plus z squared square root. Okay, so this is isotropic because the coefficient of x squared and y squared and z squared, they're all the same, and therefore it has rotational symmetry. Okay, any questions about the system that we're looking at?
So no matter which direction it oscillates, we can just say it's invariant. So
Yeah.
It doesn't matter. No,
Yeah, exactly. Okay, so now we can look at the radial differential equation because we've already solved the angular differential equation. They're just given by the spherical harmonics. The radial equation is just d squared u. I'm just going to drop all the indices, all the subscripts, and then minus L plus 1 over rho squared. Now we have switched to rho being our variable, u of rho, plus lambda minus rho squared u of rho equal to 0. Here what we have done is that E is related to lambda by this. So lambda is a dimensionless measure of energy. Okay, lambda is it's a dimensionless measure of energy. Okay. And we've also defined rho to be a dimensionless measure of distance. And there what we're doing is we say r is equal to h over m omega square root of rho. Okay, so we have just rescaled those things. You didn't have to rescale them because if you don't rescale them, you'll have to carry on, h bar, omega, m, but it's not going to help you in analyzing. So we're just like, we're just cleaning up the clutter. So from the one-dimensional harmonic oscillator, we know that, we expect our wave function to have some form like this, okay? And so we take an ansatz depending on this, okay? And again, when r goes to 0, although this actually, this potential does not go to 0, but a constant, but because it's a constant, we can always add a constant. So our, intuition for, what we did before where the potential went to 0 as r went to 0 is still valid, okay? So basically what we are saying is that we want, as rho goes to infinity, we expect u of rho to be, exponentially damped. But as rho goes to 0, we would like to assume that this goes to rho to the power L plus 1. Okay? So we combine these things to u of rho. this is the rho to the power L plus 1 and e to the power minus rho squared by 2, and then f of rho. Okay. So now we have to find out a differential equation for f of rho. That's easy. We just plug this into our differential equation, the radial differential equation, and out pops, the equation for f, which we have to solve. So this is an ODE that we have to solve. Okay, so I'm skipping steps, but these are not steps which are very difficult. So I want you to fill this in. Okay, so show. The difficult part we'll do in class. So the difficult part is solving this equation, which is actually not that very difficult. So what strategy should we take? When you look at a generic ODE, what do you say? A linear ODE. What comes to mind? A generic linear ODE, second order. If you're a first order, you'd like to try to actually integrate it, right? Directly. But with second order, what would you want to do? Any ideas? Have you solved any second order linear ordinary differential equation in any previous course?
I have solved a bunch, but none of the methods are in my I don't remember anything at this point.
Okay, sure. Anyone else? Okay, so the strategy is that, okay, we assume that this will be a very nice solution. So f is going to be a regular thing, right? So f is not going to go to infinity or anything. If you assume that, then we can say that, okay, f of rho should be given by a power series, a positive power series of rho. Okay, so we can say n goes from 0 to infinity, an rho to the power n. Okay, so this is the most simple ansatz that we can take. And then what we do is that, because all the different powers of rho as functions, they are linearly independent. They're independent functions, right? You cannot, for example, express rho squared in terms of linear power of rho, right? You can probably n higher powers of rho. You have to have a rho squared in there, right? So what we do is that we plug this into this, and then we, using the linear dependence, we equate coefficients of powers of rho to 0. Okay, because of linear independence, because of independence, each coefficient must go to 0 independently. So let's do that. So let's take df by d rho. Well, this tells us that we will get n equals to 0 to infinity, and then we have n times an rho n minus 1. But the n equals to 0 term is going to drop out because it's just multiplying, n is multiplying this, right? So we can say, okay, for the first derivative of f, the sum really starts from n equals to 1. Okay, I'm just being careful. I don't have to do, this is implied, so you don't have to do that. And then if I take the second derivative of f with respect to rho, then I'm going to have n equals to 1 to infinity, and then n times n minus 1. And then I get n rho to the power n minus 2. And here we see that n equals to 1 also does not contribute. So this is going to be starting from n equals to 2. And that's all we need. So we take this, and plug this into this equation, okay? So this is a series method. That's a very, very powerful method, okay? It's a very powerful method. It's also very simple-minded. Okay, if I do this, then the first term, let me just, copy and paste this equation for reference. Okay, the whole thing. Copy. And I'm going to paste it. And I'm going to reduce a little bit so we can fit it. Okay. So, so the first term gives me, I'm using the second derivative. So the first term gives me, it's a sum from n going to 2 to infinity. And I have n times n minus 1, an rho to the power n minus 1. What is the second term going to give me? What is the sum going to go from? So here I have, I have this thing, which is 2 times L plus 1, and then the sum. What is the limit of the sum? Limits of the sum. It's a first derivative. So here, do we have first derivative here?
Yeah, it's n equals to 1, but is
good.
it possible to go towards something else, like n equals
No,
to 2?
No, so this
Okay,
is
then.
very, this is very simple-minded. There's no magic here.
All right.
I'm just like making sure that you guys, some of you are engaged, because this is, this can be excruciatingly boring unless you are really into mathematics. And I really love this because I remember when I was undergraduate, like kind of your age, and I was studying for my final exams, and I was studying the hydrogen atom, and at some point I came across its radial equation, and by that time I had solved a few series, differential equation by series, and I said, okay, why don't I not look at the book and try to solve it myself? So I put away a couple of hours and did this very, very carefully. And then I checked, and it fit. And I was, for me, it was just like is a moment of simple, achievement. It's not earth-shattering, but it's something that, okay, mathematics works, even if I've been able to solve an equation that I haven't seen before. So so that's why I love this kind of stuff. That is very simple. There's nothing very hard, but it just works. Okay, so this is going to be this first term, and then we have to do this term. And in this term, the coefficient is plus 2, right? So we have plus 2. And again, the sum is from 1 to infinity. And we have n times a to the power n and rho to the power. What should be the power of n?
Power of n?
Yeah, well, what should be the exponent here?
B minus rho minus 1?
N minus 1, or what is the? So
yeah,
okay,
n minus
so
1.
this was n minus 1, but see that it's multiplied by rho squared.
Yeah.
Right, so it should be n plus 1.
Plus 1, yeah.
Okay, so this should be n plus 1. Okay, and then over here we have the last term. So the last term just has some constant multiplying it and a factor of rho. Okay, so that means that we have those constants, say lambda minus 2L plus 3 bracket ends, and then sum over, there is no derivative, so n goes from 0 to infinity. And then we have a of n, and we had a rho of n, but because it's being multiplied by factor of rho, this n becomes n plus 1, right? And all of this is equal to 0, okay? And now what we do is that we take the coefficient of rho equals to 0 and set it to 0. So if I look for rho equals to 0, where, what value of n do we have to take? So if n is 2 over here, this is 2. 2 minus 1 is 1, so we don't get a rho equals to 0 from here. From here, if I take n equals to 1, then of course I get rho equals to 0 here. But here I don't get a rho equals to 0 because n equals to 1 gives me rho squared. Here, n equals to 0 gives me rho to the power 1. So this is the only term that gives me rho equals to 0 for n equals to 1. Okay, is that understood?
Yes, sir.
So that means that we are going to get 2 L plus 1 N1. So N1 A1 is equal to 0. Okay. So what does it imply for the value of A1?
A1 is 0.
Right. A1 is 0. Okay. And then next we do rho to the power 1. For rho to the power 1, what should we do? Let's see. So we want to have rho to the power 1. So what value of n should we take here? We should take n equals to 2, right?
Mm-hmm.
If I take n equals to 2, then the first term is going to give me 2 times 1 times A2, right? What about this term? If I try to get n equals to 1 here, n here should also be 2, right?
What?
If n2, then I get 2 minus 1 is 1, right? So I'm trying to get rho to the power 1 in every term. And for that, I have to choose n.
Mm-hmm.
So I have to choose n equals to 2 here. If I choose n equals to 2, then the second term is going to give me 2 times L plus 1 times 2 times A2. And then what about this term? Here I cannot get, because I cannot get rho to the power 1 because it starts at n equals to 1. So this term is not going to contribute. And this term, if I get n equals to 0 here, then I get n equals to 1. So I can get A0 here. So I get from the last term plus lambda minus 2L plus 3, bracket ends, n is 0, so I get A0, and that is going to give me 0. Okay. Now you can show that A0 is fixed by normalization. Okay. And if that is the case, then this equation, if you fix A0, it gives you what A2 is. And A2 is simply given by A2 equal to minus lambda minus, within brackets, 2L plus 3 divided by 2L plus 4 times A0. So if you know A0, you know A2. So next we do rho 2. And rho 2 you can show very easily, that gives you A3 is 0. Okay, so A1 is 0, A3 is 0. So in general, it turns out A2 is given in terms of, sorry, not A2. Okay. What you can do is that in general, you can write, that equation. So what now we are going to do is that we are going to, factor all these rows from all these terms, but we are going to adjust, we are going to, play with the limits of this so that all the rows have the same power. So I will let you figure this out. It's not very hard, but it's something that will require some introspection. And as you know, physics cannot be done without introspection. So, and introspection is equal to what? time. Okay. So if you want to learn physics, you have to give it time so that you get introspection. Sorry for the, again. And so what you get is that you get n equals to 2 to infinity. And then the way you get n plus 1, n plus 2, plus 2, L plus 1, n plus 2, and the whole thing multiplying an plus 2. So this you actually get from these two terms by, if you, in those terms, what you did is that if you took n and replaced n by n plus 2, then you get these two terms. And the other terms, you have minus, and I'm just going to put everything within a big bracket, 2n minus lambda minus 2l plus 3, bracket ends. There are lots of nested brackets, so be careful, times rho to the power n plus 1, and that is equals to 0. So for every rho n plus 1, for n greater than 2 or equal to 2, we set all the coefficients equal to 0. And that means that we are relating an plus 2 to an by 2n plus 2l plus 3 minus lambda divided by, sorry, I'm taking a bit more time than usual, but I'll be done soon, okay? N plus 2, n plus 2l plus 3 a of n, okay? So this is a recursion relationship. Okay. So how do we solve recursion relationship? If I have a boundary value, I can figure out everything else. Now see that a of 1 is 0, a of 3 is 0. That means a of n is 0 for odd n, right? That's what this recursion relationship is telling us. You agree?
Yes. I think yeah.
Yeah, because this is n plus 2. So if this was a0, a1, then a3 is 0. If this is a3, this is a5 is 0. If this is a5, a7 is 0. So by dint of these two things, all the a's, if the n is odd, is 0. So our function f of rho is a function, is a power series in even powers of rho.